Hello everyone, let's analyze. So today we're going to talk about constrained extrema. So the last lecture we talked about local or relative extrema, that is the set of all local mins and maxes. But today we're going to talk about constrained minimums and maximums. And we're going to begin with this beautiful picture of a open-topped box. Suppose that I wanted to make the largest open-top box by volume given 16 square meters to work with. So my goal is to maximize volume. Of course, volume as a function of x, y, z is x times y times z. And so I want to maximize that. But my surface area of my box, that is the area of the base, x times y, plus the two sides, x, z, plus the two other sides, y, z, has to equal 16. So while I know how to find local extrema of v, that's of no help in this situation because I need to maximize v not over three-dimensional space, but over all x in the level set of S. Remember, S is my area function, and I need all x, y, z that are in this level set. In other words, the set of all solutions to this equation. So how do I maximize this function when I'm constrained to this set of x, y, z coordinates? Well, the Lagrange multipliers is here to help us. So consider the constrained optimization problem where I want to minimize or maximize f such that my constraint function g of x is equal to a constant. Right, that's exactly the scenario I was just in. Suppose f and g map some open subset of Rn to R. So in the problem I was just looking at, n was 3. Both are of class C1 on this open domain. Well, the Lagrange Multiplier Theorem says that if x naught solves the optimization problem, so if x naught is a solution, and the gradient of my constraint at x naught is non-zero, then the gradient of f at x naught and the gradient of g at x naught are parallel. In other words, there's some constant lambda for which the gradient of f at x naught is equal to lambda times the gradient of g at x naught. In other words, one is just a scaling of the other. So let's give a sketch of this proof. Suppose x naught is a solution to the constrained optimization problem. And let's illustrate our sketch by following along an example here to the right. Now, all x satisfying the constraint g of x is equal to c is called the feasibility region. Now, it's also the C level set of g. Right? It's all x such that g of x is a level, specifically the constant c. So in our example, if c is 2 and my feasibility or my constraint function is g of x is equal to the norm squared, then my feasibility region, all x, for which g of x is level at 2, is a circle. So that red circle represents my feasibility region. So, claim number 1, I claim that the direction of steepest descent of g is perpendicular to my feasibility region, which is illustrated there as a red circle in that example. So I claim that that's true. Let's take a look and see if we can visualize this idea. So this red dot represents x naught. See, there it is there. Now, what's the direction of steepest descent? Well, first, this red line is tangential to my feasibility region at x naught. Now, the reason I have a tangent there is when I say that the direction of steepest descent is perpendicular to a curve, what I mean is it's perpendicular to a tangent line to the curve. Now, this vector here is my direction of steepest descent, which is, of course, the gradient of g evaluated at x naught. Now, how do I know that that's the direction of steepest descent? Well, because I know it's the gradient. Remember, we proved that the gradient is my direction of steepest descent. And if I evaluate g in that direction, you see that takes me highest, fastest in this region. All right, so this vector here, which is again the gradient of g at x naught, is the direction of steepest descent, and we can see that it's perpendicular to a tangent line to my feasibility region. Okay, so now let's work out the math. Let gamma of t be any differentiable parameterized curve in my feasibility region. All right, so we're proving here claim 1 with the math, but hopefully we understood in the illustration why it's true. So in our example, the feasibility region is a circle. Of course, we know we can parameterize that by the radius times cosine of theta and the radius times sine of theta would parameterize a circle. Now suppose our parameterization is chosen so that gamma of 0 is x naught, which is the red dot there. Now, how do I know that such a differentiable parameterized curve exists? Well, it's a consequence of the implicit function theorem. We won't go into it, but it is guaranteed as a result of the implicit function theorem. So, since gamma of t is just a way of parameterizing some curve in my feasibility region, g along that curve must be constant. So g along that red circle is constant. Well, that implies that if I take the derivative of g of gamma of t, right, then I would get the derivative of a constant, which is 0. Now, of course, if I take that derivative, the chain rule says I get the derivative of g at gamma times the derivative of gamma. The derivative of g is the gradient of g transpose times gamma prime of t. That equals the derivative of my constant, which of course we know is 0. So if the gradient of g transpose times gamma prime is 0, then the gradient of g and gamma prime are perpendicular. Now if I evaluated t equals to 0, I get the gradient of g of gamma of 0, and gamma of 0 is x naught times gamma prime of 0. Now, gamma prime of 0 is a derivative of my curve, and the derivative of my curve is tangential to the curve, right? So we see this line is a tangent line, and gamma prime of 0 must be along this line. Now, since gamma was an arbitrary curve in my feasibility region, and gamma prime of 0 is tangential to the curve at x naught, then we can say that the direction of steepest descent, that is the gradient of g, is perpendicular to my curve, which I say right there. So claim 2, the direction of steepest descent of f, which, by the way, by the same reasoning is perpendicular to its own level set, is perpendicular to the feasibility region at x naught, and only at x naught. in this example, since x naught is a max or min of f of gamma of t. So let's see if we can see what that looks like. All right, so here we're looking at the constraint function. Let's get rid of that because this red circle is my feasibility region. So let's take a look at f, and our example f is going to be x1 squared minus x2 squared. So that looks like a saddle, but of course we're only interested in this saddle when I evaluate along this red circle. Let's do that. If I evaluate along this red circle, I get this magenta curve. So this magenta curve is f of x for x in the circle. And this magenta dot is x naught. And so we can see clearly x naught is a local maximum. In fact, it is, along with its counterpart over here, a global maximum too. So remember that this red arrow here is the gradient of g at x naught. So if I compute the gradient of f, right, of course we can see that it is, right, just a scaling of the gradient of g. And we can see that if I compute f in the direction of that gradient, that gives me the direction of steepest descent. Right, we can see that along this magenta line, which is f of the gradient, right, I increase most rapidly in this area. And of course, this increase is, or this direction is perpendicular to f of gamma of t. And the gradient of f is perpendicular to my feasibility region. Which is the second claim, that the direction of steepest descent of f, this magenta arrow, is perpendicular to my feasibility region, this red circle, at this point x naught. So the derivative of f of gamma of t is 0 because remember when t is equal to 0, I get f of x naught, and f of x naught is a local maximum. Right, we can see here that that puts me at the top. So that implies that if I take my derivative, I get the gradient of f of gamma transpose times gamma prime at t equals to 0. So that implies that the gradient of f at x naught transpose gamma prime of 0 is 0. Remember, that gamma prime of 0 is tangential to my red circle. So since the gradient of f at x naught and the gradient of g at x naught are both perpendicular at x naught, then they're parallel. And we've proven our result. Now in the case that g is k-dimensional, in other words, G maps Rn to Rk rather than Rn to R1, then there's a more general Lagrange Multiplier Theorem that says that the gradient of f at x naught is equal to the derivative of g at x naught transpose times the vector lambda. So I have a vector of Lagrange multipliers. Of course, that's equivalent to saying that the gradient of f at x naught is equal to a linear combination of gradients of the functions within g. Because, of course, g can be thought of as a list of k functions. And the gradient of f must be a linear combination of those k gradients. Later in the lecture, we'll use this more general one to derive what are known as Kirschner-Tucker or KKT conditions for quadratic programs with linear constraints. So let's return to the picture of our beautifully drawn box. We want to maximize the volume of the box so that the surface area of this box without a top is 16. So the method of Lagrange multipliers says we need to solve the gradient of V is parallel to the gradient of S, and S of x, y, z is 16. So we need to solve both of those equations. The gradient of V is yz, xz, xy. The gradient of S, y plus 2z, x plus 2z, 2 times x plus y. So if I assemble all the equations represented by star, then I get 4 equations. And of course I have 4 unknowns, x, y, z, and my Lagrange multiplier lambda. So I need to solve these 4 nonlinear functions in order to find a potential maximum. Now, we can do this by hand, and in fact we're going to, but in general, we probably wouldn't want to. What would we do typically? Well, we'd use a nonlinear equation solver rather than try and solve a system of nonlinear equations by hand. Of course, you may not think of an algorithm like Newton as an equation solver. Perhaps you think of it as a root finder. But of course, we can just take all of our right-hand sides, subtract it to the other side, and then find all x, y, z, and lambda. That would make our set of nonlinear functions 0. So how would I apply Newton to this set of nonlinear equations to get a solution? Well, I'm glad you asked. So here I have f, which is basically my start equations, but I took all of my right-hand sides and subtracted it over to my left-hand side. So I want to find a root of f. Of course, Newton's going to require a derivative or a Jacobian of f, and that's given by this matrix here as a function of x, y, z, and lambda. And I need some starting point. So notice I've picked x, y, and z to satisfy my feasibility region. I want to start on my feasibility region, and I picked some random number to be my Lagrange multiplier. And so this is going to be my starting point, and then I'm going to apply the Newton recursion. My new v equals my old v minus the Jacobian inverse times f of v. And we'll run it until we get to within 10 to the negative 10 of a root, or 100 iterations, whichever comes first. So let's find out. Let's run it. So my function at the solution I found is, as you can see, on the order of 10 to the negative 10. So that's good. It took me 12 iterations, not bad. And the solution I got is this, which gives me a volume of 6.1584. So, 24 lines of code, I've got a solution. Not bad. But if we had to solve this by hand, how would we do it? Well, let's take a look at equations 1 through 4 from the previous page. If I subtract 2 from 1, I get z times y minus x equals lambda times y minus x. If I put everything to the right-hand side, I get z minus lambda times y minus x must be 0. So either y is equal to x or z is equal to y. Well, here our path diverges. We got to pick one or the other. Let's suppose y equals x. And the case of running down what happens if z is equal to lambda, I'll let you work that one out on your own. So if I suppose that y is equal to x, in other words, I replace all my y's with x's, then equations 1 through 4 reduces to these three equations. From equation 6, if I subtract this to this side, I get x times x minus 4 lambda is 0. Now, of course, x is not 0 because 1, that would give me a box with 0 volume, which is just silly. But also because if x were 0, then equation 7 would imply that 0 is equal to 16. And let me assure you, as an expert, that 0 is not equal to 16. So that means x is equal to 4 times lambda. So then, if I replace all my x's with 4 lambda, 5 through 7 becomes 8 through 10. Of course, we see that equation 9 is a tautology, so we can get rid of it. So let's keep 8 and 10 and move it to the top. So from 8, I get 4 lambda z equals 4 lambda squared plus 2 lambda z. Subtracting it to one side, I get 2 lambda z minus 4 lambda squared is 0. Now, of course, lambda is not 0 because remember, x and y are 4 times lambda, and I can't have x and y be 0. So that would imply that z is 2 times lambda. Okay, so if I replace all my z's with 2 times lambda, then I just have an equation of lambda. It means 3 lambda squared is 1. So lambda is either 1 over the square root of 3 or negative 1 over the square root of 3. Now, lambda has to be positive because remember, x is a positive multiple of lambda. So lambda's got to be positive. So we pick the plus 1. Lambda is 1 over the square root of 3. X and y are 4 times that. And z is double that. So we have an x, a y, a z, and the lambda that solves our 4 nonlinear equations. That gives us a volume of 32 over 3 times the square root of 3, which is approximately 6.1584, exactly what the Newton algorithm gave us. So that works out. And again, where our path diverged, you should try the other route as an exercise. So let's work out another example. Let's find all global minima and maxima of this quadratic function f on the closed disk D. All right, so the closed disk, that's all x in two-dimensional space, whose norm squared is less than or equal to 2. Now, the closed disk, right, that's an inequality, so how would we treat that? Well, let's really think of that disk as 2 separate regions. The open ball of radius square root of 2 and its boundary curve, which is just the 2 level set of g if g is the norm of x squared. All right, so that's just our curve that represents the boundary of the closed disk. So first, let's find any possible extrema on the open disk, right? The open ball of radius square root of 2. So the critical points of f, right, are given by zeros of the gradient, which are solutions to 2 times the identity times x equals 1, 1. That's solved by half-half. Of course, half-half is in my feasibility region. It's in the open set of the open ball of radius square root of 2. Now, since the Hessian of f is 2 times the identity, which has 2, which is positive as both of its eigenvalues, that means xc is a local minimum, but since I have a quadratic function, it's actually a global minimum. And it's the only local minimum in the open ball. It's the only global minimum. So by continuity, it must be less than or equal to any boundary value as well. So now let's search the boundary, that is all x such that g of x is equal to 2, or the two-level set of g. Let's search the boundary for a maximum, because of course we already found a minimum in the interior. So if we have a maximum on the boundary, then the gradient of f must be a scaling of the gradient of g. So the gradient of f is 2 times the identity times x minus the vector 1, 1. Now that has to equal to lambda times the gradient of g. The gradient of g is 2 times the identity times x, and then times lambda, my Lagrange multiplier. So I need to solve this equality for x. That means x is equal to e1 plus e2 divided by 2 minus 2 lambda. Now e1 plus e2, that's the vector 1, 1, scaled by 1 over 2 minus 2 lambda. Well, that implies that x1 and x2 are the same. Unless, of course, lambda is equal to 1, then we're divided by 0 and we're in trouble. So otherwise, this is some number times the vector 1, 1. So x1 and x2 are the same number. Now, the only two coordinates on a circle of radius square root of 2 that are the same are 1, 1 and negative 1, negative 1. So f of x plus, in other words, 1, 1, is 1. F of x minus, that is the coordinates negative 1, negative 1, is 5. Okay, we have a maximum winner. And of course, f of half half is 1 half, confirming our minimum. So let's take a look at our function evaluated on a disk. All right, so we're evaluating the function on a disk. And of course, we can see that, in fact, the maximum occurs at the boundary. And we get a value of 5. And the minimum occurs right somewhere in the interior, and we get a value of 0.5. So this red dot is the location of our minimum, and this cyan dot is the location of our maximum. So minimum, maximum. Maximum is on the boundary, so it satisfies the Lagrange conditions. The minimum is in the interior, right? So it's just a critical point of our objective function. So quadratic programming is the field of optimizing quadratic forms, often over thousands or even millions of variables. So let's consider this problem coupled with linear constraints. Suppose we want to minimize or maximize f, where f is a quadratic function, with the constraint that C transpose x is equal to D. Note that the gradient of f is equal to qx plus a, and the gradient of g is equal to the matrix C. So our first order conditions and constraints are satisfied if qx plus a equals lambda times c, or c lambda. And our, of course, feasibility conditions are satisfied if C transpose X is equal to D. Of course, we could rearrange a little bit by subtracting this and subtracting this. So this set of equations, rearranged in this way, are known as the KKT for Karish-Tucker first order optimality conditions. So in order to find possible optimizers for this quadratic program with a linear constraint, we solve this linear system. Okay, so suppose f and g map some open subset of Rn to R, and suppose that they're both class CP, where P is at least 2. If we satisfy the Lagrange multiplier conditions, then I have satisfied first order optimality conditions. But how do I know if I have a maximum or a minimum, or potentially neither, a saddle? Well, let's consider this function h of lambda x is f of x minus lambda times g of x minus c. Then the gradient of h is, well, it's the partial derivative of this with respect to lambda, so that's negative g minus c. And then the derivatives with respect to x, so I get the gradient of f minus lambda times the gradient of g. Now, if lambda naught x naught is a critical point of h, then the gradient at lambda naught x naught is 0. Well, that means g of x minus c equals 0, or g of x naught equals c. So my feasibility condition is satisfied. And it also means that the gradient of f at x naught minus lambda naught times the gradient of g at x naught is 0, meaning that my Lagrange multiplier conditions are met. So if lambda naught x naught is a critical point of h, then I've satisfied both the Lagrange multiplier conditions and my constraints. Of course, h evaluated at that point would just be f of x naught, because g of x minus c would be 0. So let's illustrate this idea. Let's simplify to the case that n is 2. Suppose that the derivative of g with respect to y is not 0. All right, so n is 2, meaning that my constraint function g is a function of x and y. And of course, my constraint is that g of x comma y is equal to some constant. So suppose that when I take the partial derivative of g with respect to y, I get something non-zero. Well, then according to the implicit function theorem, right, there is a CP map phi that passes through x naught, y naught, and is on the level set of g. In other words, g of x comma phi of x is equal to c. In other words, the graph x and phi of x is in my feasibility region. So we can think of, instead of considering f of x comma y, where x and y satisfy my constraint, I'm going to think of f of x as equal to f of x comma phi of x, right? Because the graph x comma phi of x goes through my feasibility region, right? I'm guaranteed that f tilde of x satisfies my feasibility region, and now I just want to maximize or minimize f tilde. Now, one can show that if y naught x naught, if lambda naught x naught y naught is a critical point of h, then the derivative of f tilde at x naught is 0, right? So I have first order optimality conditions for f of x. Now, f of x is just, right, a regular derivative. It's a f tilde maps x to a number. And the second derivative is equal to this expression here, right? Negative 1 over this value squared times the determinant of the Hessian of h. And the Hessian of h is given by this matrix here, right? So that would be a 3 by 3 matrix, right? Because G is a function of two variables. This is a 2 by 1 vector, 1 by 2. I'm sorry, this is a 1 by 2. This is a 2 by 1. And then, of course, this is a 2 by 2 matrix. So, of course, I want to know, is this positive or negative? Right? If this entire thing is positive, then I've got a minimum. If this entire thing is negative, I've got a maximum. And of course, if it's 0, then I can't really conclude. By the way, the Hessian of H is the Hessian of F minus lambda naught times the Hessian of G. So my second derivative test for constrained extrema, again, in the case that n is equal to 2, is given by when we want to minimize or maximize f such that a constraint g is equal to a constant, right? So x and y are real numbers. Then if x naught and y naught are in the domain of f and g, and x naught, y naught is in my feasibility region, in other words, g of x naught comma y naught is c, then the determinant of this bordered Hessian at x naught, y naught is essentially going to tell us whether I have a max or min. So if the determinant of this matrix is positive, then I've got a local maximum. If it's negative, I've got a local minimum. And if it's 0, then this test is inconclusive. Now, of course, that's only the case for n equals 2. What about arbitrary n? So the second derivative test for constrained extrema, again, we're going to min or maximize some objective function f with the constraint that g of x is equal to some constant. F and g both map some open set u and Rn to R. Both are class CP, where p is at least 2. Right, because again, I'm going to be taking a second derivative. If x naught is in my feasibility region, g of x naught is c, and the gradient of g at x naught is non-zero, and the Lagrange multiplier conditions are satisfied, if I set h to be f minus lambda times the difference of my feasibility function and c, and of course, if this term is 0, that means that my feasibility conditions are met, or that lambda is 0. So if I define h in this way, then the Hessian of h is given by this matrix we call h bar, and is essentially a bordered Hessian. It's equal to this. Now again, this is a n by 1. I'm sorry, a 1 by n. This is n by 1. And then here I have the Hessian of this function here. So that's why we call it a bordered Hessian. Right, on this border and this border, we have the gradient of g at x naught. And in this kind of bottom n by n block, we have the Hessian of this function. So if delta k is the determinant of this matrix for the upper left k by k block, then if delta k is always less than 0, then x naught is a local minimum. But if it flips signs starting at k equals to 3, and of course when k is equal to 3, I get negative 1 to the 4, so positive. So if it flips signs starting with positive for k equals to 3, then negative, then positive, and so on, then I've got a local maximum. Now, if delta k are not all 0, but do not satisfy conditions 1 or 2, then I have a saddle point. So in other words, I have neither a local min nor a local max. So let's take a look at an example. Let's apply that theorem to the problem we started this lecture on, the case of maximizing the volume of an open-ended box with a constrained surface. So if I make a bordered Hessian for that problem, I get this matrix here. And of course, I want to evaluate it at x is 4 over the square root of 3, y is 4 over the square root of 3, z is 2 over the square root of 3, and lambda is 1 over the square root of 3. So if I evaluate this bordered Hessian at these values and take determinants of this upper 3 by 3 block and the upper 4 by 4 block, I get, well, I'm not going to do it by hand. Here's my bordered Hessian. Here's my x, y, z, and lambda values. Here's where I evaluate. I'm going to compute the determinant of the upper 3 by 3 and then of the whole thing. The upper 3 by 3 I get positive. In other words, negative 1 to the 3 plus 1. And for the whole thing, or the 4 by 4, I get negative. So because I went from positive to negative, x naught is a local maximum. So in fact, right, we did maximize the volume of that open-ended box, right? The x naught we found that satisfied the Lagrange conditions. The second derivative test shows that it's a maximum. Well, that's it for today.